Assalamu alaikum everyone. Welcome back to another chemistry lecture. Today we will be learning about a very important concept, the law of mass action and the derivation of the equilibrium constant. Before we understand the law, let's quickly recall what a reversible reaction is. Some chemical reaction go forward to make product, but at the same time the product can react backward to form the original reactants. This is called a reversible reaction. In this lecture, our objectives are simple and clear. Understand law of mass action, learn how to write the equilibrium constant expression, identify the conditions for equilibrium, and the last, understand how to recognize when a reaction is at equilibrium. Introduction. Chemists generally express the composition of equilibrium mixture in terms of numerical values. These values relate the amount of products to reactant at equilibrium. These values can be determined by using the relationship known as the law of mass action. Two chemists, C.M. Goldberg and P. Vaga, in 1865 proposed law of mass action. What is law of mass action? The speed, or you can say the rate of a chemical reaction depend on how much each reactant is present. The more reactant, the faster reaction. In simple word, more concentration, faster reaction. Less concentration, slower reaction. What the law of mass action states. It states that the rate at which a substance reacts is directly proportional to its active mass, and the rate at which the reaction proceeds is directly proportional to the product of the active mass of the reactant. What is active mass? The term active mass represents the concentration of reactants and product in mole per decimeter cube for a dilute solution and is expressed in terms of a square brackets. Now let's take a general reversible reaction. Here small letters are the number of moles and capital letters are the chemicals involved. Now applying the law of mass action, according to the law of mass action, the rate of forward reaction is directly proportional to the products and the rate of forward reaction is equals to Kf and where A and B rate of reverse reaction is directly proportional to the rate of reactants. Here the Kf and K are the rate constant for the forward and reverse reaction. At equilibrium, the forward and reverse reaction happens at the same speed. So we can say that the rate of forward reactions is equal to the rate of reverse reactions. Derivation of equilibrium constant Kc. Now again we can take an hypothetical example here. Now we can applying the law of mass action on this example, the rate of forward reaction and the rate of reverse reaction. At equilibrium, both rates are equal. The rate of forward reaction is equal to the rate of reverse reaction. Divide both sides by the reverse reaction. Now we can got this formula and after this the Kc is the equilibrium constant. This is our final formula. The Kc equals to Cd divided by A by B. What is equilibrium constant? Where Kc is equal to Kf divided by Kr is known as equilibrium constant and the above equation is called the equilibrium constant expression. Thus the equilibrium constant expression for any reaction can be written from its balance equation. Concentration of product is taken in the numerator and the concentration of reactant is taken in the denominator. Kc is the subscript denoted molar concentration at equilibrium. What is equilibrium constant? Equilibrium constant is defined as the ratio of product of concentration of product to the product of the concentration of reactants, each rise to the power equal to the coefficient in the balanced chemical equation. Kc is independent for the initial concentration of reactant but depend upon the temperature. The meaning of a Kc. What does the Kc really tells us? If the Kc is a large number, it means more products are formed. If the Kc is small, it means more reactants are present. The Kc is a very helpful in predicting the direction and the extent of a chemical reaction. Here are some key points to remember. Law of mass action help us understand how concentration affect reaction rate. At equilibrium, both forward and reverse reaction are equal in rate. The expression for Kc help us measure the balance between the product and reactants. Kc remains constant unless the temperature changes. So today we learn how reaction behave at equilibrium and how to use the law of mass action to derive the formula for equilibrium constant Kc. Understanding this concept is essential for solving equilibrium problem in chemistry. I hope everything is clear now. If you still have a question, feel free to ask them in the comments. Don't forget to like this video, subscribe their channel and share it with your friends. Thank you for watching and I will see you in the next lecture. Inshallah. Allah Hafiz.